Ladies and gentlemen, please continue dining as I introduce our guest speaker for today, Dr. Kimberly Budil. Dr. Budil is currently the director of Lawrence Livermore National Laboratory, where she leads a workforce of more than 8,700 employees and manages an annual operating budget of $3 billion. As director, she sets the strategic vision for the laboratory and is responsible for the successful execution of programs and operations to enhance national security through application of cutting-edge science and technology and to maintain an outstanding and diverse workforce. Dr. Budil engages with the senior leadership of the Department of Energy, National Nuclear Security Administration, and other federal agencies, as well as senior leaders across government, academia, and the private sector. She holds a PhD in Engineering and Applied Science from the University of California, Davis, and a Bachelor's of Science in Physics from the University of Illinois at Chicago. Please welcome Dr. Budil.
Thank you very much, and thank you for the opportunity to speak here today. When General Cotton's team asked if I could speak, I said, only if I can be the lunchtime keynote, because it is the most coveted slot. So I hope to bring to you something to add to the conversations we had this morning. So I'm here really representing my colleagues across the nuclear security enterprise and the National Nuclear Security Administration, our key partner to the Department of Defense and to the command here in the nuclear deterrence arena. And so what I'd like to share is our view on strategic deterrence, starting with how we think about the nuclear mission, which is our core, and then moving on to things we're doing in other areas that we believe are contributing to strategic deterrence, and perhaps a little bit of a theme around emerging and disruptive technologies, which we heard some about this morning. So I was very lucky to have the first two discussions happen prior to this keynote, because I think everyone in this room is now well steeped in the threat that we face. Now, I joined Lawrence Livermore in 1987 as a new graduate student, and the world was a very different place. So I've lived through an immense amount of change just in the arc of my career at this institution, and the world we face today is not the world we anticipated in the mid-1990s when I was joining the nuclear weapons program. So the move today, the extreme bipartisan support, the work of the Strategic Posture Commission, the work that several administrations in a row have done to strike a consensus on the path forward for nuclear is really critically important and a very heartening step forward. I used to tell people, I've watched many, many creative and innovative modernization programs for the nuclear stockpile come to Livermore to be canceled. So over the arc of that time, we saw the Advanced Concepts Program, the RNEP, the RRW, the Reliable Replacement Warhead, the W80-3 Life Extension Program, the Interoperable Warhead, and a number of other initiatives where we tried to get a consensus in the country around how to take this forward. So today's threat space has brought us to a very different place with this two-peer plus nuclear security environment. And we heard very clearly from the members of the Strategic Posture Commission this morning about the challenge that we face given the immense amount of work required to do the current program of record. So we have heard this quote many times now, the current program of record is necessary but not sufficient. But I'm going to talk to you a little bit about how to balance necessary and not sufficient in the world going forward. For me, this is a moment for us to think about not just what we need to do in this moment, but to lay the foundations for the next several decades in deterrence space. And so while it's an extremely challenging environment and the threats we face are very real, it's also a very unique opportunity for us to put ourselves on a different trajectory and to not find ourselves in the position we find ourselves in today again. So this is the shock and awe chart for the work that the Department of Defense and the National Nuclear Security Administration are undertaking at this moment. So because of this inability to achieve a consensus, we're now at a point in time where we're trying to modernize all three legs of the triad, both the delivery systems and the warheads at the same time. We're also trying to bring back online a nuclear security enterprise that has not seen full-scale production of nuclear weapons since the 1980s. So numerous capabilities have to be not just brought back online, but fully reconstituted from the ground up. We were also in a position where we had sized the nuclear enterprise for the world we thought we would find ourselves in. So roughly for the capacity to do 1.5 modernization programs, maybe 2 at one time. Today we're executing 5 and about to be embarking on a total of 7. So to say that we're inadequately capitalized to meet this moment is quite an understatement. Add to that the demographic shift we've seen in our workforce. So historically, people came to the laboratories, to the other sites in the nuclear security enterprise and spent long careers. My 35 years, it was not the exception, it was much more the norm. I just had a ceremony at the laboratory for employees that had more than 50 years of service, and there were 28 of them. So, a not insignificant number of people, really, this was a lifetime commitment to these incredibly important missions. So today we have 9,000 employees. 50% of them have been at the laboratory for less than 5 years. 75% of them have been there for less than 10 years. And our demographics are not different from the other sites in the nuclear security enterprise. So we're trying to teach a new generation, bring new capabilities online, recapitalize the production enterprise, and modernize the stockpile at the same time. So again, huge challenge, but also enormous opportunity for us to find a better way forward. So I'm going to talk to you about how I think about the nuclear component of the strategic deterrent problem. And from my perspective, it's critically important that we consider 3 lines of effort, all of which are important and all of which must be pursued in parallel. The first one is the critical importance of delivering on today's program of record. Not because it's the only thing we need to do, but because it's the demand signal that's allowing us to modernize the enterprise today. So at Livermore, we're the design agent for the W80-4 Life Extension Program and the W87-1 Warhead Modification Program, which will be the first 2 truly modernized warheads to go into the stockpile. The first 2 programs where we're making substantive changes to those systems to ensure their longevity for the missions they're expected to serve. Those are the warheads that are presenting a demand signal to our partners in the production enterprise to bring new capabilities online. And we are slowly but steadily doing just that. Last year, NNSA delivered more than 200 modernized warheads to the Department of Defense, and we hope that that pace can be continued and expanded upon. So as an example, the first pits being produced at Los Alamos, as they continue to work towards standing up their production capacity for pits, will be for the W87-1. So this year we're on track, moving smartly toward our first production unit in partnership with Los Alamos. The capabilities at the Y12 plant in Knoxville, Tennessee, again, those new facilities, the uranium processing facility, the first articles that will be produced there will be for those warheads. New capabilities are being installed at the Kansas City National Security Campus to do new types of production, introduce new manufacturing technologies that will be used in the W80-4. So it's critically important that we not disrupt this process of building and modernizing the production enterprise with the programs that we're executing today. But the second line of effort has to be thinking about the changing security environment. It's clear that we need capabilities different from what we are planning in the program of record that can augment our capabilities and our deterrent force in the near term. There are many long-term questions which we seek to address with new capabilities, but we really need to be creative and find ways to deliver new capabilities, different capabilities to meet the moment. And so addressing these near-term deterrence gaps comes with some boundary conditions, if you will. We have a limited capacity in the production enterprise for additional work. The plants are stressed to the breaking point, and we have to rely on our existing capabilities and the existing articles we have to work these deterrence issues. But there are things we can do. You heard several times today about the B61 Mod 13. The W76-2 was an example of something that was added as an interim solution to one of these near-term deterrence challenges. We're now talking about what the path forward will be for SLCM-N. It's clear that we must and we can deliver on these capabilities in the near term. The third line of effort, of course, is near and dear to everyone who works in the national security laboratories, not just because we do this work, but because we really believe this is the key to the future. And that's to lean in on the incredible science, technology, and engineering capabilities that we've developed over the 30 years of the Stockpile Stewardship Program. It really is a remarkable capability, both the tools and the people that have been developed through this program. So remember, 30 years ago, when we embarked on stockpile stewardship, it wasn't clear that we would be able to even sustain the stockpile without additional nuclear testing. Today, we know more about the science and engineering of nuclear weapons than we ever did during the development era. We have tools that far outstrip what we believed was possible when the program was launched. Computers that are more powerful, experimental tools that can do things we could only dream of in the mid-1990s. So we should be able to use these tools to find a different way forward. More than just new manufacturing methods and new materials, but new design concepts, new approaches to certification, and new ways to meet the emerging mission needs that we see. So let's talk a little bit about each one of those. So when I talk about today's program of record, I think about it as having two elements to it. We're trying to modernize the stockpile and transform the enterprise together. And they really are a system. So when we embarked on the W80-4, on the W87-1, we had to relearn how to work with our production partners. Many things can be designed in the computer that cannot be built. This is a great revelation to people who have not been called upon to build things for a while, perhaps not to the engineers in the room. As someone who's worked in both physics and engineering, I feel like I'm a swing player. I really get this. So we had to spend time rebuilding those relationships and rebuilding an understanding on both sides. So as an example of how we've worked to bridge that gap, the first picture I've shown here, this under polymers, is a partnership we struck with our colleagues in Kansas City. So Kansas City makes the non-nuclear components for our weapons, and we wanted them to make a very sophisticated polymer component for one of our systems. The only way this part could be made was through additive manufacturing. So this was a great opportunity, both to be able to achieve the design objectives of the system and to introduce really fundamentally new ways of making things into the Kansas City system. From the Kansas City perspective, this was a really challenging part to make for many, many reasons, not just new technology, but unproven technology. And while we could make parts in our laboratory setting, it's a very different business to have to make reliably certifiable parts day in and day out. So we struck a new model. We created a facility at the laboratory called the Polymer Enclave, where we built out a set of machines identical to the ones that would be in Kansas City. And we brought Kansas City engineers to work with our engineers in that facility to develop the process. So through that work, we've been able to go from a part that was not producible to relatively high producibility levels in a pretty short amount of time. And again, this was both sides learning from the other what's possible, and all of us stretching to do something we knew was really important for the future. That capability is going to change the way we think, not just about the systems we're making today, but about the systems we design and deploy in the future. At Y12, we're working in close partnership with the team there to work on uranium capabilities, and we did a different model. In that case, we emplaced a new piece of equipment in Knoxville because the idea was we had an idea for a new way to make uranium alloys, and it made more sense to demonstrate that technology close to where the work would be done so that it could be seamlessly transitioned into the production environment when we were finished. So that work has gone very well, and again, both sides had to learn and adapt and change to make it work. And then finally, for those of you who follow our work, explosives have become one of our most significant challenges. Again, we require very specialized materials with very precise requirements, and so we're working to develop new capabilities to build the systems we need and to think about ways to use these levers of new materials and new manufacturing in design in the future. So this idea of partnerships, streamlining not just the work we do, but the business processes we use is a very big theme, and the production of the parts that go into the program of record is really the vehicle by which we're starting down that path. If we go to the second one, there are a number of efforts underway today to do phase 1 studies and explore what might be possible to meet some of these near-term deterrence and assurance gaps. The goal being to utilize existing assets, given our limited capacity to do things like make new pits or make significant quantities of other nuclear parts. What can we do with the capabilities we have today and the assets we have in hand to tailor solutions for these near-term deterrence and assurance gaps? The 3 laboratories have started working together on a new concept to do basically a pilot of a rapid capabilities office within the NNSA, where we would look at some of these challenges and try to understand how we could rapidly deliver small numbers of solutions to these problems. Again, giving another lever to the system so that we can deliver interim capabilities as we get up on our feet and think toward the long term what we would like. And then finally, as I mentioned, our science tools allow us to do things that we could not do even a decade ago. So in the center panel, you see a split screen. This is sort of how we think about science at Lawrence Livermore. Since our founding, we have used advanced computation and advanced experimental science together to really inform how we think about the stockpile. So one picture on one side is of the National Ignition Facility, world's largest, most energetic laser, where we've recently achieved fusion ignition, again, creating a capability to explore the conditions that are only produced in the most extreme environments in the universe, like in the heart of operating nuclear weapons. And El Capitan, which we're currently putting online, which will be the world's first exascale computer for national security applications. So El Cap will be, when it's turned on and fully operational, the largest computer in the world. Perhaps briefly, those things change quickly, but could be as much as 2 times bigger than the current fastest computer, which is Frontier at the Oak Ridge National Laboratory. El Cap also has 30,000 GPUs in it. So if you think about applying new tools and technologies, machine learning and artificial intelligence, this machine is purpose-built to utilize those tools very effectively. So this is a vehicle for us to bring the most advanced science and technology tools to very high resolution, very high fidelity simulations, coupled with incredibly rich data from directly relevant conditions to understand how we can take steps forward. I often tell people something that they find very surprising. So if you look at the decisions we've made about the stockpile to date, and you think about making material choices or design choices for the systems we're working on today, the National Ignition Facility has actually been the key to answering those questions. So it's contributed directly to the decisions we're making about the stockpile in ways that few other experimental facilities could claim. So for the future, how can we use these tools and capabilities? Can we find ways to expand the space of designs available to us? You know, the U.S. is very lucky. We had a very rich and very diverse and very deep nuclear test program, so we have a wealth of data to work from and to ground our understanding in. But we've only begun to take excursions from today's stockpile. There's so much more we can do if we're able to fully utilize these tools and use them as a way to streamline our work. So I am legally obligated to talk about fusion ignition, since this was a centerpiece at Lawrence Livermore. It's not only an incredible scientific accomplishment, which it certainly is, it does create conditions that are moving us toward directly relevant, weapon-relevant regimes, but it's also sending a signal into the community at large. So when you think about deterrence and you think about science and technology, U.S. leadership in strategic areas of science and technology is a critical component of that. This is a part of telling our adversaries and our allies what we're capable of. It took 60 years to perfect the science, engineering, materials, chemistry, physics to achieve this result, and we are the only people in the world who've been able to get to this point. So that says something about our capacity as a country, and it says something about our capabilities as a technical leader in the world. And there are many areas where we've willingly ceded leadership in science and technology. And I would assert that continued leadership leaning in on our leadership in science and technology, in high-performance computing, in AI and machine learning, in advanced experimentation like fusion, in material science, is critically important to the posture we project to the rest of the world. And I would like to say, our last igniting shot was a gain greater than 2, a little bit over 5 megajoules. My hope before the end of the calendar year is that we're above 10 megajoules of yield. So this journey is only beginning, with the goal of planning a future facility that could get to very significant yields, hundreds of megajoule yields. So we use this very expansive science base to support a really broad range of national security missions. So at Livermore, about 2/3 of our budget is dedicated to nuclear security, to the nuclear stockpile, and the supporting science and technology capabilities. If you add in non-proliferation arms control and other nuclear security missions, it's about 3/4 of our budget. But that last quarter is very powerful. It leverages the investment we've made here, again, to build out other elements of our national security and add to the deterrence capabilities of the United States across a wide range of missions. So when I think about the lab, I think about it in these sort of concentric circles. Foundational to everything we do, of course, is people. And we have an extraordinary workforce that is really dedicated to contributing to our national security. We build upon that a set of capabilities and facilities and tools that allow us to do a wide range of things. So things like the National Ignition Facility or our computing facility, which, by the way, includes more than El Capitan. So we have about typically 5 to 8 of the top 100 computers in the world at any given time working on our missions at all classification levels. We have our core set of missions, including nuclear deterrence, threat preparedness and response, multi-domain deterrence, and climate and energy security, which is increasingly becoming a challenge in the security arena. And then within that, we have a set of what we call focus areas that are really the key questions for today in each of these areas that we seek to bring our capabilities to bear on. So in the nuclear deterrence arena, of course, the key challenge is stockpile and enterprise transformation. How can we make the system better, more capable, more agile, more responsive, and faster moving? In climate and energy security, we're really focused on resilience and adaptation. How will we deal with the changes that we're seeing in our environment? How will we secure our energy system? How will we deliver resilient infrastructure in the decades to come so that we can support our important missions? In multi-domain deterrence, which includes support for conventional munitions, cyber, space, directed energy, electronic warfare, all of the other domains, we're really trying to lean in on the concept of integrated deterrence and understand how to bring our capabilities together in new ways to help enable the Department of Defense to have the kind of asymmetric advantage that the US has always been able to bring to bear. And then in threat preparedness and response, we're focused on bioresilience. We learned many lessons through the pandemic, one of which is we need to be much faster to respond to an emergent threat. And particularly in the security arena, being able to respond immediately to an engineered threat is key to showing our adversaries that it's not worthwhile. We need to be resilient in the face of those threats so that they make the choice not to deploy such capabilities against us. And we have a long history of doing all of these missions. So as a centerpiece of our efforts in integrated deterrence, we've been focusing on some of our combat simulation and other modeling and simulation tools to understand how the battle space will operate with new tools and capabilities in it. This is an example from our joint conflict and tactical simulation software. We're working with other partners in the DoD enterprise to really understand how to bring tools together in new ways so that there can be good, high-resolution planning and understanding of how different capabilities could work together. And I show the Blue 129 just as an exemplar of what we can do to show we can do fast. So this is a low collateral damage conventional munition we developed that went from emergent operational need to deployment in the field in 18 months. So it's not a fundamental limit of the system that it takes 10 years to deliver a new capability. So how do we bring these tools and this mindset to bear in our nuclear mission is one of the things we're looking at. We need to be in contact with the thinkers on deterrence questions. How do we understand the environment we work in and work with partners across the government to shape our capabilities in the right way? So our Center for Global Security Research really allows us to bring our technology community together with policymakers to help lay the foundations for good and informed policymaking in the government. We do very significant amount of work in space, and we have a long legacy in space science. We've been turning those assets increasingly to defense missions. This is an example of a small monolithic optic telescope that we have built that can fly on a small satellite to do surveillance missions, essentially, in space. These are capabilities that build on the work that we've done in our laser program over many years to develop the capability to build very unique types of optical systems, including the ability to additively manufacture optical systems. So again, bringing our unique capabilities to bear in a critical domain where we have a lot of expertise to deliver new types of equipment. This is an example from our critical infrastructure work, where we're focused on trying to secure cyber-physical systems. So if you think about things like the grid and our energy systems, many of the components in them were in place before cybersecurity was a significant concern. So our teams are focused on developing strategies to both monitor and make resilient, essentially self-healing, these types of cyber-physical systems. So the picture at left is of our Skyfall test range, which allows us to put physical hardware in the loop with large-scale simulations. So we can simulate the entire grid and put in place real hardware from utilities to begin to understand how it would respond to adversary attacks and how to make them more resilient. The picture at the right is Livermore, which is our Lego city. Every summer we have about 100 interns come in to learn about cybersecurity, and they use this essentially as a test range. So it's a fully wired city, and they run challenges to see if they can both bring down and bring back up the electrical grid in Livermore. It's a pretty cool program. So we're turning out a new generation of cyber infrastructure experts. And we're focused on trying to understand, again, what's happening in the climate, what are the implications from a security perspective, and how can we use our knowledge and tools and technology today to adapt to or mitigate the worst impacts that we see coming. So a very significant effort to understand how to decarbonize the environment, but again, also how to make our systems more resilient and to ensure that we understand what the security implications can be of some of the worst impacts that we predict with our high-fidelity climate models. And I'm going to finish with this example because I think this is a good one that shows what's possible. So about a decade ago, we started working very hard, actually during the Obama administration's Cancer Moonshot effort, to understand what might be possible using high-performance computing to change the way we design drugs and therapeutics. So the team began using our very large-scale computers, which can run simulations that are large enough, they allow us to model the very large and complex molecules required to understand both biology and countermeasures. And they began building a toolkit that would allow us to design molecules to specific threats. We also began in our engineering program to build platforms, engineered platforms, that would allow you to do much of the testing that we currently rely on either animal models or human testing to do much earlier in the process. So we could screen molecules for efficacy and safety and move them very rapidly from in silico and on chip into human trials at a very high degree of sophistication. So this program has been going for about 10 years. Today, the flagship effort is a partnership with the Department of Defense called GUIDE, which has been focused on design and redesign of antibodies. So during the pandemic, this team was able to redesign antibody therapies for newly emergent variants of COVID with 1 to 2 weeks of compute time. Now, it still took 4 months to test them and to get them into the clinic, but we were able to shorten the timeline very dramatically. Today, this team is looking at not only remodeling antibodies for new variants, they're doing projections of how viruses will evolve so they can predict what the likely variants are, and then designing antibodies that are effective against many variants. So in their most recent work, they were able to predict 22 possible variants of a virus that would emerge, and they were able to design antibodies that would be effective against 19 of them. So one antibody effective against 19 variants. So this is the future of resilience in the biology space, where we'll be able to develop drugs and therapeutics on a very rapid time scale, very tailored to the specific threat at hand, and open up real opportunities to change the way we think about biopreparedness. So with that, I'm going to just spend 1 minute on AI. It was only mentioned once or twice today, but it's certainly been the biggest topic of conversation for us for quite some time. Now, we've been working and thinking about artificial intelligence and machine learning for decades. This is not a new topic. But the emergence of generative artificial intelligence over the last year has been an extraordinary change in the way we think about these tools and technologies. I particularly liked this chart, which I saw in someone else's talk, about how quickly this technology is pervading everything that we do. So this is time to adoption by 50 million users for various technologies over time. And yes, the population of the world has changed over this time, but not to the degree that would explain this change. So in less than 2 months, ChatGPT had more than 100 million users. So what will these tools enable? What will we be able to do with these tools? But perhaps more importantly, what will others be able to do with these tools? So at the Department of Energy, the 17 national laboratories have come together with a department to put together an initiative called FAST, Frontiers of AI for Science, Security, and Technology. Yes. It's a terrible acronym. To really begin to understand how we can bring our computing and computational science capabilities to bear, not just in how we will use AI, but how others might use AI. So one of the first examples leading out of the executive order that came out earlier this year from the White House was to establish a program for red teaming within the National Nuclear Security Administration, again, to begin to look at what these models might be capable of and how others might be exploiting them for gain. We're currently working to bring some significant resources to bear in this arena so that we can build out the specialized compute at all levels of classification to begin to understand how these tools can transform our work in national security. And I really have seen over the last 5 years in our internal research and development portfolio, we went from having 1 or 2 projects that were focused on AI-based technologies or machine learning to having about 90% of the projects that get proposed have some component of machine learning and AI. So it's already changing the way we work, but if you think about the challenges we face, designing new materials or building in new manufacturing methods that have on-machine inspection, born qualified opportunities, or thinking about the range of designs and design optimization, these tools have the capability to really change the way we think about our mission space. And so we're moving very quickly to begin to adopt them and to try to understand how they're going to change and shape the national security space around the world. So with that, I'm going to close, and thank you for your attention. I'm surprised at the level of silence. I hope it's not sleep. And I look forward to your questions. Thank you. And while you're thinking about questions, there was one point I wanted to make that didn't come up earlier, and it's related to this last point about FAST. So there's a huge amount of investment in the private sector in tools and technologies like AI, and that's very important, and that's a big part of why the US is leading in some of these technology areas. But it's critically important that there be public sector investment in these technologies as well. So this is not to say that the companies working on these technologies aren't going to find great ways to use them and interesting models for how to deploy them, but you really do want entities working in the public interest to understand what the limits are and where there should be guidelines and guardrails around these technologies. So I really encourage us to think deeply about what public-private partnerships mean in this environment and how we can ensure that the public investment maintains pace with the speed at which the private sector is moving out in some of these areas. So can people ask questions, or they're not supposed to? One question? All right, it was so clear. Thank you so much.